Okay, so fission and fusion, those are the topic for this video. And we touched on it slightly when we were looking at the unit workbook, and it was at the bottom, and a minute here, at the bottom of page 6. I told you then that all of those reactions were not spontaneous. They are not natural decay because essentially something's being added to them. And right now, fission and fusion are also artificial. They are not natural. They are man-made unless we're talking about stars. So on Earth, they are always man-made. So I am going to go ahead and talk about that briefly. I'm on page 9 of your unit workbook, and you have just the PowerPoint, the important ones there. So let me go ahead and share that. Okay, so artificial radioactivity, like I said, is done in a lab or in a particle accelerator. This is the Large Hadron Collider, which it borders France and Switzerland. I've actually been there. It was so exciting. It was so much fun. So they take protons. This is 17 miles in circumference, which is really very big. And they go ahead and shoot protons or subatomic particles around this at the speed of light, and then they have them collide. And the collision occurs in here, and then they have these detectors that detect what type of particles are being emitted when the collision happens. So elements that have an atomic number of over 92 are all artificially made. There are a couple that are less than 92. Promethium is one of them. They are called, so not promethium, but anything over 92 would be a transuranium element because uranium is 92. And that's the heaviest naturally occurring element. You might have heard, these are sometimes called, so there's the Large Hadron Collider, they're called accelerators, atom smashers, nuclear reactors are different. So this is the tunnel. So these are 2 people working on the collider itself. The particles are they go at the speed of light because of magnets. So magnets are positioned, and they're huge magnets. It's amazing. If we'd had time, if we were in class, you would have done another project on this one. So fun. Okay, so fission. Fission is what happens in a nuclear power plant. So when we go back and you think about this right here, this is from The Simpsons, you know, Bart works here, and everybody kind of freaks out over what the substance is that's coming out of these stacks. I think people think that it's radioactive. It is not. It is just water. So fission and fusion, both, they do not produce any greenhouse gases. They are very carbon neutral, which is great. There are things that aren't good with fission, like meltdowns and Chernobyl, but in terms of greenhouse gases and the environment, it's not so bad. This is what happens during fission. So I take a uranium atom, I throw a neutron at it, and it splits. When it splits, it also produces 3 more neutrons right here, which then can hit some neighboring uranium atoms. And then they split. And this becomes a huge chain reaction. So what happens during Chernobyl, what had happened is that chain reaction got out of control, and therefore there was a meltdown. There was just so much energy that they couldn't control it. In a nuclear reactor, they use what's called control rods to absorb these neutrons. So you can essentially, I don't have a very good picture handy, but you take, essentially think of a big bathtub full of nuclear fuel. And in the bathtub, you can dip these rods into the bathtub to absorb these neutrons. So if you absorb some of those neutrons, then they wouldn't be able to hit the neighboring uranium atom, and therefore it would slow down this reaction, and you would end up producing less energy. All right, so let me give you the equation for this. So this is written out more in a diagram than an equation, so let me show you that. And I'll put it down here. Oops. There it is. Okay, so here's your equation. So here's uranium-235, right? 92 is its atomic number. here's my neutron, there's the neutron, and it's actually ending up, oh, my numbers are slightly different, but it's still barium and krypton. And if you notice the numbers on top, so 144 plus 89 plus 3, because right, there's 3 of these neutrons, so 3 times 1, that's going to end up equaling 236. Okay. On the bottom, 56 plus 36 plus 0, that's going to end up equaling 92. Alrighty. So that's how fission works. And again, remember the top numbers have to equal from one side to the other, and the bottom numbers do as well. Okay, so let's just real quick check something out here. Oh yeah, let me go back. Stop sharing here. Okay, so this is on OneNote. And so this is a great example of how this chain reaction happens. So there's the nuclei, the one nuclei hitting the one atom of uranium just about now. So the more ping pong balls you see here, that you can correlate with the more energy being produced. So if you think about a nuclear reactor, if you can't control this, oh my gosh, that's an awful lot of energy and an awful lot of heat being built up. And then, yeah, it would not be a good situation. And that's a lot of gamma radiation being released. Okay, I'm gonna stop that there. Okay, so let's go back. If you guys are interested, 2 things. There is a link on OneNote for Chernobyl, and that's like a 30-minute docudrama on how Chernobyl happened. If you want something more in-depth, the docu-series that's on HBO called Chernobyl, that is amazing. It gives you a really good perspective on how it all happened. Okay, so that is fission. Fusion on the other, oh wait, let's go back. So fission, so notice big nuclei. I'm fizzing it, I'm splitting it into very smaller pieces, and then those get converted into smaller pieces. Mass is being converted into energy, because remember we learned about the law of conservation of mass. Well, in this case, this doesn't happen. The mass of your products is a lot less than the mass of your reactants, and therefore, you know, what happened to that mass? Well, it turns out that that mass was converted to energy. And this is E equals mc squared. So this is Einstein. Okay, so fusion. Let's talk about the opposite. Fusion is when I take 2 small nuclei and I form a bigger one. I produce energy with this as well. Both of them are chain reactions. So this is also a chain reaction. It doesn't happen like the ping pongs. Let me give you the screenshot for this one. Try to do this so I wouldn't have to write it, because I know that that's painful for everybody. Okay, so here, this is deuterium. Deuterium is hydrogen 2. So you can see I have a proton and a neutron. So there's my 2, and of course the 1 is the proton. And I'm gonna combine it with tritium. So again, 2 neutrons, 1 proton. And again, the top numbers, I've got 5 on top here. 4 plus 1 is 5 here. I've got 2 on the bottom, I have 2 on the bottom. It produces a helium nucleus as well as a neutron. So this is a chain reaction because that neutron can come around and combine with another deuterium to form more tritium. Deuterium. Deuterium is called heavy water, and you can find it in heavy water. Heavy water has, instead of a hydrogen 1, it has a hydrogen 2. And it can be found, it's a certain percentage of the world's water, and it's a fairly high number. This is the one that's your limiting factor. So when this neutron comes off, if it can combine with more deuterium, then that's making more tritium, which is what you need to combine again with the deuterium to form helium. So this is also a chain reaction, not as obvious as the other one. So when we compare these, so fission, we've talked about Chernobyl. We have the possibility for meltdown. It does produce a bunch of hazardous waste. And since, let's see, about 2008, we've got 56,000 metric tons of hazardous nuclear radioactive waste. Bill Gates has actually got a project called, I think it's called TerraPower, if you want to look it up, where he's trying to figure out a way, and I think they've been somewhat successful, or they were successful actually, trying to find a way to use this nuclear waste and produce more energy with it. And actually, they were going to try it out in China, and then there were tariffs put on it, so they had to bail. They built a plant and everything, and I think they had to stop whatever they were doing and refigure some stuff. There is more than one possible equation for this. Versus fusion, there's really only one. So when you think about it, with fusion, I'm taking 2 positive nuclei. And in this case, hydrogens are my littlest possible charge, right? Just +1. And I got to combine those. Those 2 positives do not want to come together. So this takes a lot of temperature, a high heat, high pressure in order to get those 2 positives to come together. Once they do, they still also convert matter to energy, and there's little to no hazardous waste. There's no reactor cores, there's nothing to worry about here, versus over here, there's a lot of it. So speaking of Chernobyl again, effective distance, it's good that we're distant. I was in high school, I think it was 86. I was in high school during Chernobyl. It was pretty freaky. If you were closer to it, and if you watch either of those documentaries, you'll see that, yeah, people definitely felt it. And it wasn't like, well, some people, the closer they were, the worse the effect. You can use shields. There are, when you go to the dentist, they put a lead shield on your chest when you have your x-rays taken of your teeth, and that's to protect every other part of your body. So shielding, we've talked about this already, right? The shields are just these things right here, and they protect you from radiation exposure. Okay, that's fission and fusion. Go ahead, there's an assignment, just a quick check. So go ahead and do that, and I'll see you guys soon. Bye.